Yes. So last time we had a prime number P, which remains fixed. And we had defined the Hilbert symbol from QP star cross QP star to Z star. It takes a pair A, comma B to AB, P. So let me do something here. Hello, can you still hear me?
Yes, yes, sir.
Hello?
Yes, yes.
Oh, okay, good. So this is better for me. Now, one of the basic properties of the Hilbert symbol was that it's symmetric and that it's multiplicative. So of course, with symmetry and this multiplicativity, it becomes bi-multiplicative, right? Multiplicative in the first variable as well. In particular, because it takes values in plus minus 1, AB squared, which is going to be ABP times ABP, that's equal to 1, because the square of anything is equal to 1. Right? So that's these are the basic properties of the Hilbert symbol. And then there were these two things which he proved, saying that A minus AP is always equal to 1. And this Steinberg property, that A minus A comma 1 minus A, P is equal to 1. Of course, this makes sense only for A different from 1. Okay. Now, even if you don't recall what the definition of this Hilbert symbol was, here are these two things which will allow you to compute it. For P different from 2 and for P equal to 2, all you need to remember is that ABP is equal to 1 if A and B are both units. That's when P is different from 2. And APP is lambda P of A whenever A is a unit. So by multiplicativity, these two cases suffice to compute ABP for all AB in QP star instead of just ZP star, right? These two combined allow you to compute ABP, the Hilbert symbol, for all A and B in QP star. For Q2 star, something slightly different happens. AB2 is, even when A and B are both units, it's not equal to 1, as in this case here. It's minus 1 to the power epsilon 4A times epsilon 4B. And what is this epsilon 4? This epsilon 4 is just epsilon 4 of a unit. A in Z2 star is just A minus 1 upon 2 mod 2. So it's 0 or 1 depending upon whether A is, so very explicitly epsilon 2, there's no epsilon 2, epsilon 4 of A is 0 or 1, and it's 0 if A is congruent to 1 mod 2 mod 4, and it's congruent to 1 mod 2 if A is congruent to minus 1 mod 4. Okay, similarly, A2, A comma 2 at 2 is minus 1 to the power epsilon 8 plus of A, where epsilon 8 plus is this thing here. It takes A to A squared minus 1 upon 8. one should perhaps say mod 2. Okay, so of course, every here also A is in Z2 star. So whenever A is in Z2 star, one can check that A squared minus 1 upon 8 is in Z2, and therefore its value mod 2 makes sense, because from Z2 you have this map to Z2 modulo 2 Z2. A or X going to X mod 2. Okay, so these formulae allow you to compute the Hilbert symbol in all cases. For example, we had checked that P comma P at P is plus 1 if P is an odd prime congruent to 1 modulo 4. It's minus 1 if P is an odd prime congruent to minus 1 modulo 4, and it's equal to 2 if P is equal to 2. Okay, so these things, as I've said, allow you to compute ABP in all cases by just writing A as a power of P times a unit, and you do the same thing for B, where U and V are now in ZP star, and M and N are of course in Z. Then you just expand, and because of these 3 elementary cases, this case here and these 2 cases or these 2 cases allow you to compute ABP for all AB in QP star. Okay. And we had also computed the quadratic characters of QP star. That was the Hilbert symbol, and now of course the Hilbert symbol was defined in terms of these quadratic characters. So for a prime P different from 2, this QP star had 3 quadratic characters, which we had called nu P, lambda P, and of course the product of these two, nu P times lambda P. And this nu P, we had called it the unramified quadratic character. For P equal to 2, there are 7 quadratic characters. Here they are. Nu 2, this is the unramified one. We haven't defined what it means for something to be unramified. We are just calling it unramified for the time being. And there are these 6 ramified characters, quadratic characters, lambda 4, nu 2 times lambda 4. For example, lambda 4, what is it? For an A, it's just minus 1 to the power A minus 1 upon 2, where this A has to be in Z2 star. Or in fact, so, and we extend it to, so this makes sense only for A in Z2 star, but we extend it to all of Q2 star by saying that 2 to the n times A is just lambda 4 of A. That's why a choice of this uniformizer is necessary in order to extend lambda 4, lambda 8 plus 2 Q2 star. And the same applies for this lambda P, of course. Initially, it's defined on ZP star. Then we extend it to QP star by, sending P times N times U, P to the N times U to just U here, and applying lambda P to this U. So these are the quadratic characters of QP star. So today what we are going to discuss are 2 or 3 things. The first one is, what are the quadratic extensions of QP? Then how are these quadratic extensions related to quadratic characters of QP star, the ones we have just listed, these, and how are these quadratic extensions connected to the Hilbert symbol. Okay, so that's the plan for today. Right. So now, for the time being, let K be any field of characteristic different from 2. Then we have its multiplicative group K star, and we can go modulo the squares in K star. So we'll get K star modulo K star to the power 2. Of course, this group has to be written multiplicatively, but one should think of it as a vector space over the field F2, the field with 2 elements. Okay, so just as if you have any commutative group A and you have any prime number L, so suppose that we are writing it multiplicatively, then we can form this group A modulo A to the L, and this should be viewed as an FL space, vector space over the field FL. So this is the special case L equal to 2 of what I have explained here. So, this follows from either Kumar theory, or that's a fancy way of saying it, or just by completing the square. So what is the assertion? It says that whenever I have a field K of characteristic different from 2, and I look at this F2 space, so this vector space will have some lines in it. So this is the set of all lines in this vector space. The assertion is that it's in bijection with the set of all quadratic extensions of your field K. And what is the map which gives this bijection? It takes a line, a vector subspace of dimension 1. So it's just a subgroup of order 2. Takes this subgroup D to K adjoined the square roots of everything in D. Okay? And what is the map in the other direction? If I'm given a quadratic extension L, how do I get a line in K star modulo K star squares? You just take this L, so you have a map from K star to L star, that's the inclusion. From this, you can go to L star modulo L star squares. Of course, this will factor through K star modulo squares. So you get this map here, and this will have a certain kernel. So that kernel is the one to which L is being sent. That kernel can be checked, is going to be a subgroup of order 2. So, as I said, this is just all this is a translation of the fact that if your characteristic is different from 2, then you can complete the square, because here you need to divide by 2. Given a polynomial x squared plus bx plus c, you can write it as x squared plus twice b by 2 over x plus b by 2 whole squared minus b by 2 whole squared plus c, right? And that becomes something squared minus something else. Okay. Okay. So I don't know. So here is an explicit example. If you take K to be your field R of real numbers, then K star modulo squares is just plus minus 1. And if you take K to be Fp, but P has to be different from 2 because our characteristic has to be different from 2, then this group has order 2, because case this is cyclic of order p minus 1, right? Everybody knows this, right? And if I take k equal to c, of course, this group is trivial. In any case, let's take k to be this field QP. So that gives me all the quadratic extensions of QP, because I've already determined what QP star, we know what QP star modulo squares is. So what is it? It consists of just the non-trivial elements are root u minus p and minus up when p is odd, where u is any unit which is not a square. This is the same as saying that lambda p of that unit is minus 1. Lambda p, remember, is you first reduce it modulo p and then you see whether it's a square or not. But it amounts to checking whether this unit is a square to begin with, right? Because of Hensel's lemma, being a square modulo p is the same as being a square in the units when p is different from 2. Okay, so when p is equal to 2, q2 star modulo squares, recall, it consists of, there has to be, okay, so as I keep on insisting, let's think of it as a F2 space, and it's generated by, it has a basis consisting of 3 elements as an F2 space, and those 3 elements are minus 1, minus 3, minus 1, and 2. So it's over F2, it's generated by these 3 elements. So how many quadratic extensions does it have? So that's the order of this group. Quadratic extensions correspond to non-trivial elements. So it's not 2 to the 8, it's 2 to the 3, which is 8. That's the order of this group. And so the number of quadratic extensions is 2 to the 8, 2 to the 8, 2 to the 8 minus 1. So it's 2 cubed minus 1, which is 7. And here are these 7, right? You adjoin the square root of minus 3, or the square root of minus 1, or the square root of 3, or the square root of 2, or of minus 6, or of minus 2, or of 6. These are the 7 quadratic extensions of Q2. And I've written them in 3 rows. There's a reason for doing it, which need not concern us for the time being. Okay. So it has something to do with the ramification filtration, and this gives you the unramified extension and so on. But we have not defined these things, so we just take it that there are 7 quadratic extensions of Q2, and these are the ones. Okay. Right. Now I want to recall what the norm map is. So let's do it only for quadratic extensions. So we have a field of characteristic different from 2 and a quadratic extension L of k. Then of course we can write it as k adjoined square root of a for some a in k star, which is not in k star squares. Okay, and the norm map takes x plus y root alpha root a. So x, y are of course in K, and this is a typical element of L, right? So it takes this element x plus y root a to x squared minus a y squared. So this is of course the product of x minus y root a and its conjugate, which is x plus y root a. So that's what the norm of this element is. For example, if I take r adjoint root of -1, then the norm of this element here is just x squared plus y squared. And what's the image of the norm map? It's strictly positive real numbers. It's a subgroup of index 2 in R star. Okay. So this is just an example. And this is what the norm map is in general for quadratic extensions. Over fields of characteristic different from 2. So here's the main theorem for today. What does it say? It says that there is a unique bijection between these two sets. The first set is a set of all quadratic extensions of QP. And the set is a set of all quadratic characters of QP star. Of course, there are many bijections between these two sets because this has either 3 or 7 elements, and this also has 3 or 7 elements. So maybe there are 3 factorial or 7 factorial bijections between these things. But we are saying that there's a unique bijection having some property. And what is that property? So the property is that if it takes a quadratic extension E to the quadratic character chi of E, then the kernel of this quadratic character, kernel makes sense because this is a homomorphism, right? Should be equal to the image of the norm map from E to QP. That is the requirement. So there's a, what I allow you to think about or to internalize this statement for a few seconds. You have these two sets. There are many bijections between these two sets, but there's only one bijection which has this fantastic property that the kernel of the quadratic character is equal to the image of the norm map from the quadratic extension. So it's a bijection between quadratic extensions and quadratic characters. Of course, quadratic extensions of QP and quadratic characters of QP star. So there's a unique bijection. And of course, if I have a bijection, I have an induced map of groups. I mean, these are groups. Quadratic extensions were in bijection with the non-trivial elements of this group, and quadratic characters are by definition non-trivial elements of this group. So if I have this bijection here, then of course I get a map by sending the trivial element here to the trivial element here. So I'll get a bijection between these two groups. And the other claim is that this is not just a bijection, it's actually an isomorphism of groups. Okay? So maybe I should rephrase this. How should I rephrase this? Maybe, yeah. Well, how about this? Yeah, okay. We will come to it. I think we'll do it later. So let's once again look at the statement. It says that the set of quadratic extensions of QP and the set of quadratic characters of QP star are in this canonical bijection characterized by this property. Okay. So here is the bijection which I've written down for odd P. It makes the quadratic extension. So here of course U is in ZP star and it's not a square. So that gives you a quadratic extension QP root U. I make it correspond to the unramified quadratic character. Then there's the extension QP root minus P. I make it correspond to the quadratic character lambda P. Of course, QP star modulo squares as a vector space over F2 is generated by just two, has a basis consisting of two elements, U and minus P. I could have taken P, but that would have made the formulae more complicated. So I've taken minus P, which makes the bijection easier to write down. And the third quadratic extension of QP is QP adjoint square root of minus UP. And of course, I make it correspond to the quadratic character nu P times lambda P. So that's what I do for P odd. And for P equal to 2, I have these 7 quadratic extensions on the left, the 7 quadratic characters on the right, and I have this bijection between them, right? So what we need to do now, so we have given the bijection, or we have given a bijection. What we need to check is that this property holds for this bijection. That was supposed to be the property which characterizes this bijection, right? Okay, so let's start checking. So you might have to consider different cases. Let's first consider the case where the prime P is odd and UE is this quadratic extension QP root U, where U is of course an element here like this, and I'd made this quadratic extension correspond to the quadratic character nu P. So that's what I've written here. The quadratic character which corresponds to this extension is nu P. So I have to check that the kernel of nu P is equal to the image. Is it equal to the image of the norm map from this E? Okay. So if you recall what the kernel of nu P is, so nu P was, okay, so the kernel consists precisely of those elements of QP star whose valuation is even. What the definition of nu P tells you, right? Because nu P, how was it defined? You have QP star, the valuation VP takes you to Z, and then you can go to Z modulo 2Z, and this is isomorphic to Z star. And this was the map nu P. So nu P is +1 or -1 if and only if VP of, so let's call it X, VP of X is equal, is +1 if it's 0 mod 2, and VP of nu p of x is -1 if vp of x is congruent to 1 mod 2. So that's what the kernel consists of precisely those things whose valuation is even. So we have to check that something is in the image of the norm map if and only if the valuation is even, and we will be done, right? Because that's what we have. The kernel consists of those elements of QP star whose valuation is even, and we want to show that the image of this norm map, right, is also characterized by those elements of QP star whose valuation is even. Okay, so let's take an A which is a norm, which is in the image of this norm map. By definition, so this is the norm map, right? It takes x plus y root u to x squared minus u y squared, right? So if A is in the image, means that A is equal to x squared minus uy squared for some xy in QP. Now you take A to the other side, and by the definition of the Hilbert symbol, this condition is equivalent to the fact that this Hilbert symbol should be equal to 1. That's how the Hilbert symbol is connected to the norm map. So this A is a norm if and only if this Hilbert symbol is equal to 1. So now you use, of course, you can multiply both sides, both of these things by A squared, because you don't change the value of the Hilbert symbol. What I'm saying is that A t squared B at P is equal to A B P for any t in QP star. So I multiply it by A squared, and then I get this. Then I can expand it. So this is the first factor, and this is the second factor. But A minus A at P is always equal to 1, right? That's one of the things which we had proved about the Hilbert symbol. So it remains to check that this is equal to 1 only if the valuation of A is even. And that's checking which every one of you should be able to do, right? So we have proved that for P odd and for E, the following quadratic extension, QP root U, for E equal to this, and chi E to be this new P, we have shown that the kernel of this chi E is equal to the image of the norm map from E to QP. Now we can do the same things, do a similar checking for the other cases. Let's consider the case P equal to 2 and E equal to Q2 adjoined root minus 3. Okay, and the quadratic character which we have assigned to this quadratic extension was nu2. So as before, the kernel of nu2 consists of precisely those elements whose valuation is even. And we have to check that the image of the norm map consists of precisely the same elements. Okay, So let's take an element A in Q2 star. What does it mean for it to be in the image of the norm map? We have to check that this A belongs to the image of the norm map if and only if its valuation is even. Okay, so start with, suppose it's in the image. By definition, this is the norm map from Q2 root minus 3 star to Q2 star. It takes x plus root of minus 3 times y to x squared plus 3y squared, right? So if it's in the image of the norm map, if it's a norm, then there exist x and y such that A is equal to x squared plus 3y squared. As before, being of this form is the same as saying that this Hilbert symbol is equal to 1. So we can expand it, and this is the first factor, this is the second factor. The first factor is always equal to 1 because x minus x at 2 or at p is always equal to 1. So we have to check that the second factor is 1 if and only if the valuation is even. And this is a checking which you can do. And here is what is involved in doing this checking. Okay, so maybe I should take just one more random example. So let's consider the case where the prime p is odd and I take E to be this quadratic extension. QP adjoint root of minus p. And I'd said the quadratic character corresponding to this quadratic extension is lambda p. So what is the kernel of lambda p? Of course, it consists of, so the valuation is allowed to be arbitrary, but this unit has to be a square. So it consists of, the kernel of lambda p consists of p to the power n times u squared, where u is in zp star. Okay, so there's a kernel of lambda p. And we have to check whether it's equal to the image of the norm map from E. E is now this quadratic extension. Okay, so something is the norm, something is a norm if and only if there exists xy in QP such that this A is equal to x squared plus p y squared. So as before, this translates as this Hilbert symbol being equal to 1. So I can multiply by a squared to get this equal to 1, and then expand. This part is always equal to 1. So the condition becomes finally that this should be equal to 1. And this is equal to 1 if and only if this alpha is this unit is a square. Okay, so these are actually, in a sense, we have already done these checkings, but in a different sort of context. So one final case, let's take p equal to 2. Let's take this quadratic extension, and the quadratic character corresponding to this quadratic extension was this lambda 8 plus. So for an A in Q2 star, we have to check that it's in the image of the norm map. It's a norm if and only, of course, this A can be written like this, which is the same as saying that A2 at 2 should be equal to 1, which is the same as saying that lambda 8 plus of A should be equal to 1, because we had explicitly computed what A2 at 2 is, right? So it was in terms of lambda 8 plus. And this is the same as saying that A is in the kernel of this lambda 8 plus. This is equal to lambda 8 plus. Yeah. Okay. Now, as I said, what we are given is a bijection between two sets, quadratic extensions and quadratic characters. By taking the trivial element, here in this group, quadratic extensions correspond to non-trivial elements. And in this group, the quadratic characters correspond to the non-trivial elements. So you get a map of groups, a map of sets by sending the trivial element here to the trivial element here. And the claim is that it's a homomorphism of groups. Now that's completely clear because of the way we had defined it. For example, let's see, where was the definition? Yeah. So you can see clearly that this quadratic extension corresponds to the element u bar. This quadratic extension corresponds to the element minus p bar. And this one corresponds to the product of these things, u bar times minus p bar, right? This element is being sent to this character. This is being sent to this character. And the product of these two elements is being sent to the product of these two characters, right? And the same is happening here. The product of these two elements, look at these two, that's here, and similar, the product of these two quadratic characters is this one. Or you could look at this one, and so maybe I use a different colored pen. I use this one and this one. So this one is being sent to lambda 4, and this one is being sent to lambda 8 plus. Is minus 2 being sent to lambda 4 times lambda 8 plus, right? Let's see. Yeah, here it is. So that it's a homomorphism of groups is kind of completely, it's built into the bijection. Okay. So one of the corollaries of this is that for every quadratic character, quadratic extension E of QP, what is the index of the image of the norm map inside QP star? So that index is equal to 2. Because this image, this is equal to the kernel of chi E. This chi E is a quadratic character, and the kernel therefore has index 2. Okay. So basically what we have done is that we have given sort of canonical bijections between these 4 different kinds of sets. What are the 4 sets? The first set E is a set of all quadratic extensions of QP. The second set H is the set of all index 2 subgroups of this group. The third set L is a set of order 2 subgroups of the same group. These are subgroups of index 2 here and order 2 here. And finally, the fourth set Q is a set of all quadratic characters of QP star. And we have given bijections between these 4 sets. What are the bijections? What is the bijection from E to H? It takes a quadratic extension to the image of the norm map from that quadratic extension. And that gives you a subgroup of index 2, right? That's the corollary that we had proved here. That's a bijection. What is the bijection from the subgroups of index 2 to subgroups of index of order 2? So that's the orthogonal with respect to the Hilbert pair. Okay. So from subgroups of order 2 to quadratic extensions, you just take that subgroup and you adjoin the square roots of everything in that subgroup. So this, of course, stands for QP. You adjoin the square root of everything such that X is in QP star and X bar, so which is in QP star modulo squares, should belong to this particular L. That's what this notation means. You adjoin the square roots of everything in L, so to speak. What is the bijection from Q, the set of quadratic characters, to the set of index 2 subgroups? You take your quadratic character, its kernel is an index 2 subgroup of QP star. You go modulo the squares and you get an index 2 subgroup of QP star modulo squares, right? Okay. So that was all I had to say about the Hilbert symbol. Basically, what this Hilbert symbol does is, so I promise that I'll do it later. So here is the time to do it. Well, the summary of what the Hilbert symbol does, the summary is that there's a unique bijection so from QP star modulo QP star squares to, let me put it this way, the Galois group of M over QP. So M is equal to, you take QP and you adjoin both a square root of U and a square root of minus P. So this is when P is different from 2 and U is as before. And when P is equal to 2, you adjoin a square root of minus 3, a square root of minus 1, and a square root of 2. That's your M. So there's a unique bijection like this, such that not the kernel, such that for every quadratic extension of QP, right? The quadratic extension is E. And of course, it will have to be contained in M. For every such quadratic extension E, the kernel of the map from QP star to, I can go modulo the squares. And then there's this map, which I'm going to call rho. This is, so it's M over QP. And this E is a subfield. So the Galois group of E over QP is a quotient of the Galois group of M over QP. So I'll get a composite map from QP to this. The kernel of this map should be equal to the image of the norm map from E to QP, of course, E star. So this is the summary of what this Hilbert symbol does. It gives you, so this here is a Galois group of a certain extension M of QP. It's actually the maximal abelian extension of exponent 2. We'll come to it again. In any case, here is a canonical Galois extension of QP, and M is the Galois group of this extension. Not M. You have the Galois group of this extension. N is that extension, right? And what we are doing is giving an isomorphism of a known group with this Galois group, and we are saying that there's a unique isomorphism having this property, that the kernel of this composite should be equal to the image of the norm map. Okay, so to put it in a slightly wider context, let's switch to pure algebra for a few minutes. Pure algebra, which is Galois theory. Okay, so we have a field K and a finite extension L of K. Then, of course, we can talk about the group of all automorphisms of L, which leave, so here, all automorphisms of the field L, which leave every element X of K fixed. So that's a group aut KL. Let's just call it G for short. So given a field K and a finite extension L, you have the G, and you have the subfield of fixed points. It consists of all X in L, such that sigma X is equal to X for all sigma in G. Of course, K is contained in this set of fixed points because this is what we had required in the definition itself. Okay, and of course, this it's a subset of L because it's the set of all X and L satisfying some condition. So I assume that you people are somewhat familiar with the definition of a Gamba extension. If you're not, for today, the working definition is that L over K is going to be called Galois if this here, this extension here, this is an equality. You have a field K, you have a finite extension L, you have the group G of all K automorphisms of L. If the fixed field of that G in L, I mean G acting on L, has a certain fixed field which is denoted G to the power L. It's not the set of all maps from to L, of course. It's not that. It's defined here. Set of all elements in L which are fixed by every element of G. If that fixed field is equal to K, then you say that this extension is Galois. Okay, so here are some very simple examples. If you have the K is if your K is the field of real numbers, then the field of complex numbers is a Galois extension. And if your field K is the field of rational numbers, then Q adjoint root N is a Galois extension for every square free integer N. There's some problem. Oh goodness, what happened? Now what is well, my pencil has stopped working, but let's continue like that. Okay, so do tell me if you're not able to follow something. There's some problem with my pencil now. Anyway, so these are some examples of Gamba extensions. These first three are quadratic extensions, which means they are extensions of degree 2, C over R, or Q root N over Q, or QP root D over P, you know, where D is in QP star, but not a square. And so if you, here is a more interesting example. You have Q adjoint e to the 2 pi I upon n, which is an extension of Q. And the Gamba group here can be identified with Z mod NZ star. Okay. So this is the notion of a Gamba extension of a field. It's a finite extension having the property that the fixed points of the group of K automorphisms is equal to K. And here are some examples. Now, the separable algebraic closure of a field K, denoted K tilde, is, informally speaking, an extension of K which sort of admits an embedding from every Gamba extension L. Okay, so if you have, so K tilde, I'm defining what it is. I'm calling it the separable algebraic closure of K, but it's in some sense the smallest extension containing, but containing is within quotes, every Gamba extension of K. So what does that mean? Slightly more precisely, it's an algebraic extension of K which admits an embedding, a K embedding from every finite Gamba extension. Oh, now it started working. Okay. So K tilde is what I'm going to define. It's something which admits K embedding from every finite Gamba extension L of K. And if there's another extension omega having this property, so containing within quotes every Gamba extension in this sense, so it admits a embedding, right? It doesn't have an embedding. It doesn't have to be unique or anything like that. So if there's another extension omega having this property, then there's an embedding of K tilde in omega. So in short, K tilde is the smallest or a smallest extension of K containing all Gamba extensions of K. Okay, and then we define what is called the Gamba group of K tilde over K, denoted by GK, is a group of all K automorphisms of K tilde, where, and actually it's a sort of pro-finite group. Remember in the first talk, we had talked about projective limits of inverse systems of groups. And if it's a finite inverse system of finite groups, then the inverse limit is called a pro-finite group. So this GK is a pro-finite group, is the inverse limit of all Gamba groups where L is a finite extension of K contained in K tilde and it's Gamba over K. Okay, so basically, given a field K, we have its separable algebraic closure, and we have GK, which is the group of all K automorphisms of K tilde. But the problem is, given your field K, you want to explicitly determine what K tilde is, what this group GK is, and what the action of GK on K tilde is. More precisely, these three questions amount to the following. So for K tilde, you have to specify a subset S of K tilde, which sort of generates K tilde. Just as for C, it's generated by just one element. You join a square root of -1. Or in the case of P equal to 2, M was generated by 3 elements, right? It was minus root of -3, root of -1, root of 2. But M is not K tilde. It's not Q2 tilde. It's just a small extension of Q2. It's not the separable algebraic closure of Q2. We are now taking a very big extension, K and K tilde. It's sort of the largest possible algebraic extension is and separable. Okay, forget about probability. But what one would like to do is determine a subset of K tilde such that K tilde is the smallest extension of K containing those elements. So in some sense, give a system of generators of K tilde. Then there was this group GK. We would like to give an explicit isomorphism of groups from a known group A to GK. So when you solve for some, if you solve an equation, you have an unknown X, and finally you say X is equal to 3. So this is a known thing, and this is the unknown, and you have solved the equation. Here is an unknown group. If you have an unknown group like Z mod 2 or Z hat, Z hat is the group which is the product over ZL of product over L of all ZL, where L, of course, is a prime. So these can be considered to be known groups, and this GK is an unknown group. What we have to do is to give an isomorphism from a known group to this GK. That's what it would mean to determine GK. But this GK doesn't come just as a group. It comes with an action on this field K tilde. So, and K tilde is generated by these elements of, once you have given a system of generators, we would like to say what the action of sigma A, it's called sigma, yeah, sigma A on a generator S is. So give a formula for sigma A S. These are the three things we would like to do for an arbitrary field. Of course, this is completely hopeless. You can't possibly think of doing any such thing in general, but that's the idea. You would like to do it for arithmetically interesting fields. And arithmetically interesting fields are these field R of real numbers, the finite fields FP. So here are the answers for these two cases. And perhaps these are the only cases essentially where we can give a simple answer, apart from one or two other cases, right? So if K is equal to R, then you can take S to be just one element, square root of -1. And you can take A to be Z star. A is what? A known group with which you are going to give an isomorphism with the Galois group of this. So, and what is the isomorphism sigma? It takes the generator. So this is generated by -1, right? It takes the generator and it acts on this generator of the field and gives you the generator with a minus sign. So this is just what you know. I mean, that's how complex conjugation acts on this number, which is called I very often. Okay. So here is a slightly more interesting example. You take K to be this finite field FP, and then you can take S to be the nth roots of 1 for every n which is prime to P. If you adjoin all these nth roots of 1, all these nth roots of unity to FP, you are going to get FP tilde. So this is FP tilde is FP adjoin nth roots of 1, where n is not going to 0 mod P. And the known group A with which the Galois group is going to be isomorphic is Z hat. As I said, it's the product of all ZLs. And finally, you have to explain how this Z hat acts on these generators of FP tilde. So this 1 is a generator of Z hat, and these are generators of FP tilde. So sigma 1 acting on this just takes it to the pth power.
So you are saying that the Galois group of FP tilde over FP is Z hat.
Sorry, say it again.
You are saying that the Galois group.
Why is the Galois group?
You said A is the known
Yeah,
group.
I'm
Z
saying.
hat.
Yeah, I'm saying if you take this.
Yes.
This Galois group, it's equal to Z hat. Yes, that's right. So I've not proved it, but this is usually proved in courses on Galois theory.
Okay.
So take my word for it today.
Okay.
In fact, what is interesting is if you take any finite field, K is any finite field, and if I take K tilde and I look at the Galois group of K tilde over K, that is equal to Z hat. Yeah. So the only difference is going to be when I take the difference, when I take an arbitrary K is going to be that instead of the power P here, I'll get the power Q, where Q is the number of elements in this K. So, yeah. Okay, so the major problem in number theory is, of course, what happens when K is equal to Q. Even in this case, of course, there's absolutely nobody who is capable of giving you a system of generators for K tilde and giving you an isomorphism of GK with a known group. I mean, all this is out of reach for a couple of centuries. So we'll have to do something less hard. So we will have to, anyway, okay. So, but this, it's a good thing to keep in mind, that what you would like to understand is this is called the absolute Galois group of this field K. K is Q. Understanding the absolute Galois group of Q is the major problem in number theory. Okay, so when you cannot understand a group, you might want to understand some small pieces or quotients of that group. So if you have a group G, then you have the maximal abelian quotient of that group. For example, well, so it's defined as you take G and you take elements of this form, X, Y, X, Y, these are called commutators. And you take the subgroup generated by all such commutators. That's called the derived subgroup of your group G, and it's denoted DG. So it turns out to be a normal subgroup, and when you take the quotient G modulo DG, it's called the maximal abelian quotient of G. It has the property that it's abelian, and if there is some other abelian quotient of G, then it factors through this particular quotient. And there's a certain universal property which you can write down, and which you must have, I don't know whether you have done it in your courses in group theory, but I mean, or what it says is that you have G and you have this quotient A. If you have, so this is a surjection, and this is, if there's some other surjection where B is commutative, then there's a unique map like this, which makes this triangle commute. So that's a maximal abelian quotient. Even understanding the maximal abelian quotient of absolute Galois groups is not an easy matter. So sometimes you take even a smaller quotient. So you choose an integer n, and you go modulo the nth powers. So this is going to be the maximal abelian quotient of exponent dividing n. Okay. So for example, if your group is, I don't know, well, yeah, okay, let's see. So here, maybe here is an exercise. So if your A is this group ZP star, and what is A modulo A to the n? You have to consider various n's, right? N is some integer greater than 1, and you have to find out what A modulo A to the n is. A is this group ZP star. Okay, so this is a summary of what we have done. You have a field K, you have its separable algebraic closure K tilde, you have the absolute Galois group, which is the group of all K automorphisms of K tilde. And if you are not able to understand this group, all of it, then you look at its maximal abelian quotient. And if you're not even able to understand what this maximal abelian quotient is, you further cut it down and you look at the maximal abelian quotient of exponent dividing n for some n, right? And these quotients are also themselves Galois groups of some extensions. So instead of, for K tilde, we had these K tilde and GK, we had these three problems. What is K tilde? What is GK? What is the action of GK on K tilde? These were the three problems. So there are these now simpler versions of these three problems. They are here in this in this circle now. What are they? The first problem would be, what is this K abelian? What is this group AK? And what is the action of AK on K abelian? In other words, you have to specify a subset which generates K abelian element, and you have to give an isomorphism of AK with some known group, and then you have to specify the action of this known group on K abelian. So these are the problems which class field theory solves for fields like QP and other fields, not just QP, but other fields which are called local fields. Class field theory solves these three problems for the maximal abelian extension. Okay, more precisely, what local class field theory does is it gives an explicit isomorphism of AK with a known group. And what is called explicit class field theory solves the other two problems, namely specifies the generators for K abelian and gives the action of AK on these generators. Okay, so of course we are not going to do it today or even by the end of this course. I'm not sure. We'll do some particular cases, which is that we'll replace the maximal abelian extension by the maximal abelian extension of exponent n. And even then, we'll take n to be some things like 2 or what is this? Yeah, we'll take n to be just 2 or p minus 1, etc. We might even take n to be equal to p. That's going to be quite an achievement. So in this case, again, we have to specify some generators for these fields, some isomorphism of this group with an explicit group, and specify the action of this group on this field. Okay. Now I have to recall Kumar theory and Artistry theory to a small extent. Now Kumar theory deals with, these are all algebra theories, which is to say they work for an arbitrary field K. K is a field, and n is an integer greater than 1. And we suppose that K has an element, K star has an element of order n. This is the hypothesis under which Kumar theory works. So then Kumar theory tells you that the maximal abelian extension of K of exponent dividing n is just obtained by adjoining the nth roots of everything in K star. Similarly, there's this thing called the Artistry theory, where you have an arbitrary field K, but it's of characteristic different from 0. Then it has to be a prime number, and it tells you what the maximal abelian extension of exponent P is, where P is the characteristic of this field. It says that this maximal abelian extension of exponent P is obtained from K by adjoining P inverse of X. P is this thing which is sometimes called the Weierstrass P. It's a German way of writing P, old German way of writing P. So, and it stands for this polynomial, t to the P minus t. What is this? Yeah. Right. Yeah. So, you adjoin to K the roots of this polynomial et minus x for all x in K. These are the roots, and the roots are being denoted by this. And Artistry theory tells you that that gives you the maximal abelian extension of K of exponent P. Okay. So now let's come back to our local fields QP, where P is a prime, and let's take n equal to 2. Now this satisfies the Kumar hypothesis because QP contains -1. You know, the Kumar hypothesis requires K star to have an element of order n. Our n here is 2, and this is an element of order 2 in QP star. Okay, so according to Kumar theory, the maximal abelian extension of exponent 2, let's call it M for short, is given by just adjoining a square root of u and a square root of -p when p is odd, and the square roots of -3, -1, and 2 when p is equal to 2. Okay, so here is the restatement of what we have done, and it says that when you take M to be this maximal abelian extension of QP of exponent 2, the Galois group of M over QP, there is a unique isomorphism rho from QP star modulo squares. I mean, this is of course a known group now, right? QP is given to you, so you know the multiplicative group, you know the squares, you know what the quotient is. If you are given an isomorphism rho of this quotient with the Galois group of M over QP, then you are determining this group. And the theorem is that there's a unique isomorphism which has this following property, such that for every quadratic extension E of QP in M, this is the isomorphism rho here. You have this isomorphism, but this extension is contained in M. So there's a map from Galois group of M over QP, Galois group of E over QP for every quadratic extension E. And this complete map from QP star to the Galois group of E over QP should have kernel equal to the image of the norm map from E star. So this is what, that's a restatement of what we have been doing today. And where the Hilbert symbol enter this picture? So it says that, so if we have identified the Galois group with this group, right? So that was only one of the problems. I didn't find out what the Galois group is. The third problem was, what is the action of the Galois group on M in this case? So M is generated by elements of this kind. The Galois group consists of elements of this kind, and the action of this on this is given by this, where this, of course, is the Hilbert symbol. Okay. So this is basically what, I mean, as I've been saying, the translations of this isomorphism that we had given between this group and the group of quadratic characters, essentially, of QP star, such that the kernel of the quadratic character corresponding to an A is in QP star, is the image of the norm map from QP root A. Okay. So now as I said, that was a case n equal to 2, and we are later probably going to do the case n equal to p minus 1, because the Kumar hypothesis is satisfied with k equal to qp and n equal to p minus 1 as well. Why? Because we had this r star. The r star is the set of roots of t to the p minus 1 in qp. So that, and we saw that it has exactly p minus 1 elements, and that's how we had defined this omega, which was a map from fp star to r star. This was the, I don't know whether I'd call it the Teichmüller character or not, but that's what it is sometimes called. So, so we had shown that this R star is a subgroup of QP star of order P minus 1, and therefore the Kumar hypothesis holds, and the Kumar theory, in which case, will tell you that the maximal abelian extension of QP of exponent dividing P minus 1 is obtained from QP by adjoining the square root, not square roots, P minus 1th roots of everything in QP star. Okay, so if we call M this extension, then the theorem is going to be, it's a future theorem, that there's a unique isomorphism rho between QP star modulo P minus 1th powers and the Galois group of this M over QP. M is this extension here, such that for every intermediate extension, the kernel of this composite map is equal to the image of the norm map. So that determines, that just gives you what this G is. It doesn't tell you what the action of G on M is. Kumar theory also tells you what M is, right? I mean, here is, so there were three questions. What is M, G, and the action of G on M? There are three things. So this we have done. That's just Kumar theory. This is what this future theorem will do. And now I have to tell you what the action of G on M is going to be. And here it is. It's exactly going to be in terms of this gamma AB that we had defined earlier. So if I have an A in QP star, rho of A is an element of G, right? And these are the generators of M. So an element of G acting on an element of M is, this is the result. It's this omega of gamma AB bar times the same element. It multiplies each element by this thing here. And what is this thing? Omega of gamma AB bar is explained here. So first, gamma AB was this expression which we had used in order to define the Hilbert symbol earlier. But now, instead of taking the lambda p of this expression, which is what we did to define the Hilbert symbol, I just take its reduction modulo p. So I get an element of fp star. This here is a unit, right? So its reduction modulo p is an element of fp star. And then every element of fp star has a lift omega of that element, which is in r star. So that's a lift of, and this is what This is how G acts on M. Okay, so this is a foretaste of what we might do much later in the course. But right now, we are going to leave these periodic fields, and from tomorrow onwards, we'll come to these simpler fields called K power series T, where K itself is a finite field. So that's day after tomorrow onwards for a couple of lectures. Okay, then. Are there any questions? Any questions? If not, I'll end the session. Right?